later if you need. The first part of the exam is going to be 35 multiple choice, worth only 1 point each. The second part of the exam is going to be 11 short answer, and these are worth a variable amount of points, but totaling 25 points. The third part of the exam is going to be choose 6 of 8 for your response, worth 6 points each, totaling 36. And then there's 1 for response that's mandatory that you have to do, worth 4 points. Now, let's see, are we on? Oh, good, we're good.
Yeah, connected.
Yep.
Got it.
You got it on there?
Mm-hmm.
Device number 6 or 11?
Yeah, 6.
Sweet, finally. Okay, that took forever. All right, so when we need this to display, Elliot, just switch it out. Yeah, unplug it. What does it?
This is 6.
Okay. All right, at this point, we let it go. That's really funny. So I want to give you a list of topics that you could, I would suggest to study for the math problems. I'm going to give you 10 topics, okay? There are only 8 questions. You only have to choose 6 of them. I'm giving you 10. So I would recommend looking at all 10 of them. The 8 problems are within those 10. I'll tell you right now. Okay, so you can jot these topics down. I'm just gonna state them. I'm not going to be writing every one of them down.
Do you have a problem that has like 2 questions?
There's a possibility that could happen. I'm not going to tell you yes or no, but you could expect that, sure, you should be able to do something like that. All right, first, circular motion. Guys, I'm listening again. 10 topics. Of these 10 topics, 8 of them are definitely on there mathematically, of 6, which of 6 you have to do. Circular motion, momentum, conservation of momentum, really. Okay, circular motion, conservation of momentum, heat transfer, which is what we did with the most recent stuff on the test with Q equals MC delta T, that stuff. Conservation of energy, meaning like potential to kinetic and springs. Simple harmonic motion. Electric forces. Projectile motion. Pressure. Electrical resistance and power. And a circuit problem. Okay, that should be 10 total topics there. Here, you want to read them off one more time?
Circular motion, conservation of momentum, heat transfer, conservation of energy, simple harmonic motion, electric forces, projectile motion, pressure, electrical resistance, power, and circuit.
Okay, 10 total there. If you can cover those 10 and do example problems, maybe look at problem sets or look at some old homeworks in those sections. Those are your mathematical, just to give you like a heads up. Now, everything else obviously we've done is fair game for any question outside of the mathematical. So you're going to have the short answer in the middle, which are just simply like a sentence or two. Please do not waste your time writing the 3 paragraphs when you can answer in 2 sentences. Okay, some of you still write way too much in the middle portion. If you can answer it quickly and you answer it fully, that's fine. You don't have to go into more detail. Some of you have been losing points. You have all the right work, and then you state too much, and then what you state at the end is wrong. So I have to take off points as a result. So please, if you've answered the question sufficiently, don't go on forever. Multiple choice, 35 questions. Of the 35, I would say between 25 to 30 of them are straight conceptual. The other like 5 to 10 could involve some minimal math where it's like the K value doubles what happens to the period of oscillations. So you have to look at direct and indirect relationships and that stuff. Which is very simple math, where your answer is going to be like the square of some number or the square root, but you still have to be able to do that. Okay? What else?
The last problem, is it just...
That's within these. Yeah, this is just it's not going to be a hard problem, trust me. 25% first semester, 75% second semester. What else? Average on the final last year from the senior class, which was a junior class last year, was an 81.5, like around an 82. I expect it to be the same this year, at least. I took off about 4 questions in length compared to last year's, the short answer ones, but added about 4 or 5 multiple choice from last year. Multiple choice are a lot quicker, and the ones that I added that were not on last year's are actually easier, I think, than the ones I had. So I helped you out a little bit in that sense for time. Okay, because last year that was the only concern I had from a few students said, I missed like one question and get time to do it at the end.
So like, how do you think that we should kind of go about studying the first semester? Because I guess like studying how many, like 25 chapters is just kind of too much.
Yeah, absolutely.
So like, how do you think that we would go about like just reviewing the notes, like major
Okay.
comments?
Yeah. So like for example, what's a topic in the first semester that you need to know? Like something in physics that's so like it happens all the time. Projectile motion, something you got to know the idea, the concepts behind it, and maybe a mathematical one. What else? What's another one? Forces. You got to know Newton's 3 laws. You have to know about forces. You have to. It's used in buoyancy. It's used in electric fields. So the concepts that are the major ones, momentum was a big topic in the first semester. Understanding the idea. Conservation of energy, a big topic in the first semester. So the ideas behind them. Now, if you're studying and you feel confused about something, you can watch the video. You can watch the video that I recorded, but please don't try and watch like every video. It's not possible. So my recommendation I gave the other class were several things. First, look at your notes. In your notes, you have not only math problems, you have a lot of notes you write on the side. Those notes on the side will help you for conceptual stuff. Second, look at the problem sets. Either look at yours or my solutions on Moodle. Third, look at your labs. Your labs have a lot of conceptual stuff. The labs are very, very minimal when it comes to mathematical calculations or problems, more just simple calculations for the math and labs. The labs are good for conceptual. You could use the textbook if you'd like, if there's a section you want to look at. And then, after that, there's not much more you have left in study. Okay, but I would go in that order for those things. But if you're looking for math problems, then you should look at your problem set. If you're looking for conceptual, look at your labs. For your notes, you could find both. Okay, you could find both in your notes. Other questions about the exam? Remember, please, over the weekend, if you have a question, email me. I'll record a quick answer. I'll maybe write something, record it, and send you a quick video. Or maybe I'll even link you to a video that I found that works for answering your question if it's conceptual. If it's specifically a mathematical problem you're troubled with, then email me and maybe I'll just solve it for you, go through all the steps, and you can read through it or listen to it. Please don't email me Tuesday night at like 11 o'clock expecting to get a video back in the next 10 minutes when your test is Wednesday morning. So be reasonable at the same time, okay? If you email me on Saturday, I might not reply till Sunday, but I'll get back to you, okay? I'll just give you an idea or a heads up so you know that. All right, let's pause for a quick second with this. Before I give you your grades and stuff, Nina, why don't you quickly come up and we'll talk about what you're doing with yours down the morning. So, and it's over here, if you guys could just take a look over on the side. So you want to explain the setup and the idea behind it first, Nina?
Okay, so we have these 2 containers made out of styrofoam. One of them is filled with cold ice water, and the other one is filled with warmer water that was microwaved. And then we have an aluminum bar in between them to transfer heat.
Okay, you get the idea so far what we're doing? All right, now this is our starting point right here. This was at 12:15. In the last class, this is what happened over time. Now, there's several things that we talked about in the other class. What are some things that would affect the rate of heat transfer? What would affect the rate of heat transfer? There's several parameters in this experiment that would involve. Give me one.
I think maybe like the temperatures are really drastically different.
Good. The delta T. First one is the big one. The temperatures are a big difference. They'll probably start going toward each other quickly. As they get closer, though, they'll start going slower and slower because they're not that far apart. Second. Yeah, so what did we say it was? It was metal, right? Why do we use metal?
It absorbs heat really well, so it transfers.
It transfers heat very well. Good. It's got a very high K value. And you're welcome to, it might be still working. In the other class, you can actually feel heat on one of them. Now, let's cool down now. When we started earlier, this one was the hot one, I think, right? Yeah. You could feel the heat like actually flowing. This was hot and this was ice cold over here. And over time, though, it's starting to balance. What else? There's 2 other things I can think of.
Mass.
What is it?
Mass.
Mass. Actually, that's the third thing. The amount of water in each. If there's more cold water than hot water, chances are the hot water's temperature will drop drastically before the cold water starts to increase. Initially, it was ice water. So what had to happen in the beginning to all that ice? Yeah, it has to melt. You have to phase change. So the energy in the beginning from the heat probably caused the ice to melt in the beginning first. What is the container made out of? God bless you. Why? Is air and styrofoam. Air is a good insulator. Gas in general is a good insulator. So here you have insulation that's keeping the room temperature from really affecting this. What if there wasn't a good insulator around it? What would happen? What would happen if there was not a good insulator to the temperatures of these really hot and really cold fluids? Sure? Yeah, they get to room temperature pretty quickly. So let's analyze for a quick second. Initially, what I thought was going to happen, I was wrong, so I hypothesized that I was not right about this. I thought that the cold wasn't going to change much because there was a lot of ice. And I thought the heat would drop. Turned out that the cold jumped in the beginning more than the hot did. So we went up 1 degree in hot and down 4 in cold. And then after that, there was a difference of 5. This was a difference of 8. Here then we saw that it started to equalize itself. So this went up by 2. This also went up by 2. Now, since 1245, a lot of time has elapsed. And
Yeah, it's
Put
because
them all
the
up
periods are wrong.
sorry. So what did we start this one as? Did you take a temperature measurement again? So let's do one now. So let's do 240. And then we'll go to each 4 of these. And over time, what's going to happen, obviously, folks? What's going to happen over time? Anybody, just pull it out. Yeah, the temperatures eventually will become equal to one another. See, that's what's really going to happen eventually. What do we have right now?
32 and 21.
All right, so we're getting close. And I had the other class hypothesize what they thought the final equilibrium temperature would be, and they were just picking arbitrarily. What could affect the final temperature? What could affect the final equilibrium temperature? There's one major thing that should affect the final equilibrium temperature. No? Somebody kind of mentioned it already. The amount of mass in each of the fluids will really affect it the most. The delta T is one thing, but the amount of mass in each will change, will affect how much the hot and cold will change respectively. If you have a lot of cold water, the final thermal temperature, or thermal equilibrium temperature, will probably be lower than room temperature. If you have a lot of hot water to start, it might be a little bit higher. But over time, what will happen is these will both meet at the temperature that is room temperature. What's room temperature in degrees Celsius? Anyone know? I don't know off the top of my head. I know in Fahrenheit it's like around like 70 degrees or so at room temperature. That's why when you put your thermostat on there, it's always around 70. Even in the winter, you heat up the house to about 70.
Would it be like 14, 13?
I don't know. I'm asking. I'm not sure. Yeah. What is that converted? Convert 70. I'm guessing it'll be somewhere between these two numbers here, simply because they're going to probably meet at that room temperature.
21.
It's 21, that's what it says. So right now, the cold one has already gotten up to room temperature. The hotter water that started is still a little bit above. So they might settle out a little bit above room temperature then. And then after a while, they might both drop to room temperature once they both cool down in the insulated containers. That makes sense, the ideas here? Okay, this concept, the conceptual knowledge is very important for your test. Multiple choice, for your response possibility for this, knowing Q equals MC delta T, knowing Q equals ML. Some of you have to review those problems. And when I give you your last test, you'll be able to see if you had struggles on that. Okay, there were 3 parts to that. There was a increase in temperature, a phase change, and an increase in temperature. It was Q1, Q2, and Q3 on your test. All right, now Elliot's going to do something over here. He's going to demonstrate. And you want to describe what you're doing? Do you want me to?
So basically what this is talking about is how certain materials will strip another material of electrons while they will give it to it through reduction. I've always been testing it through reduction. So you put up the...
I'm going to, yes. Give me 1 second.
Attaching a sensor to the cup in the center. And we're also grounding on the plate on the left side.
Give me 1 second before you start. Hold on. I'm just trying to get this loaded. It's not loading.
Ground myself.
There we go.
So we're going to zero the sensor, so we're at...
So remember nanocoulombs, guys, and microcoulombs? So this is what it's picking up. And he just calibrates on the side of the sensor, which zeroes it out. It pretty much gets rid of all the charge. It picks like a reference line, the potential energy is 0.
So first I'm going to rub this cloth on it, and then I'm going to put it in the center of the cup without touching it. If you touch it, it'll transfer through conduction to it.
So what happened here? Maybe just gonna go up a little bit. Maybe. We're seeing a jump in charge. So what could you say as a statement based on what he just did? If this charge went up that it was feeling, this is going up in the positive direction, right? What does that mean then? If the rod is inducing a positive charge on this, what do we call this? What's the term for it? I forget the actual name. On the Faraday valve. If the rod is inducing a positive charge on the Faraday valve, what does that mean? What's taking what's electrons? Remember, the Faraday pail is not touching the rod. There's no electron transfer between the rod and the pail. All we're seeing is that the pail itself is sensing a positive charge in its region. What does that mean again? You have to think about how electricity flows.
Is it pushing, positive pushes the electrons away?
Okay, but go back to the cloth and the actual rod first. Hold on, go back to the cloth
That the
first.
rod's losing electrons.
Why would the rod be losing electrons?
Because it's being transferred to the pump.
So the cloth is taking electrons from the rod over here, so the rod is positively charged. When you put it into the actual pail is sensing the actual charge on the rod itself. Okay, you want to zero it out again?
Yeah. Alright, so we're going to take wool this time and rub it along the rod. And then you put it in.
And clearly, what do you see here? Why do you notice when you put a wool sweater on in the winter, what happens? Ever get like a little spark? Does it ever happen? Seriously. Put like a wool sweater over your hair real quick. The wool rushing past your hair, you'll get a little bit of a charge and you'll feel that spark. You put a cotton shirt on, you don't notice it as much. See how much more electricity wool transfers, how many electrons jumped? And notice it's negative now? So what happened this time? The pail's picking up a negative charge from the rod. What do you know?
Is the wool giving or taking electrons?
It's a 50-50 shot down there. Yeah, it's giving electrons. Clearly, this is becoming more negative, which means the rod is becoming more negative. So the wool transferred its electrons to the rod itself. Okay, this is what we're doing. Remember we talked about induction? Induction is when you bring something near the object, and then you ground it, and then it remains charged afterward. That's what's happening here. This is induction. So you're seeing the actual physical charges occurring. That make sense? Okay, the idea, the concept is important. We didn't do anything with this mathematically, if you remember. We didn't do anything with conduction and induction mathematically. The mathematical portion we did with this was with like electric fields. Okay, but this is really good for your multiple choice and your short answer. You have about, I think, 2 problems about induction and polarization and conduction with electrical signals. Thanks. All right, next. A lot today. I know I keep saying that. Next, what I want to do, let me give you your tests. While I give you your tests, what I'll do is I'll call you up for your quarter 4 grades so you can see them at the same time. Okay?